So far in this series, I haven't really delved deeply into creating circuits because we haven't needed to put circuits together yet since we're simply communicating with the USART. But I have been using this board, and what if you did want to create a circuit using the FTDI 232? This would be the way to interface a STM32 or an ARM chip that doesn't have the capability of connecting a USB to a computer. So this would be a good exercise for me to show you how to implement the FTDI chip with the STM32 microcontroller. And in future videos in this series, I will show the circuit in a program called KiCAD, draw the circuit schematic, and design the PCB layout. And I think that would be a good way to show the circuit schematics and the PCBs as a part of every video that I use or I change components on the design or showing a particular feature of the microcontroller where I'm using an external device or component.
I know how frustrated you all have been trying to get your project from development to a cost-effective product under the Arduino environment. You've torn all of your shirts to pieces with these frustrations, so let me help you cover yourself back up with my new shirt and hoodie. I program in bare metal. Link in the description.
So the first thing I'm going to do is look up the datasheet for this particular integrated circuit. This is the FTDI 232. You can see that there's a few components on this board that this chip may actually need and may not need. So let's take a look at the datasheet and specifically look at the application notes. We need to make sure that we're getting the correct datasheet, so we need to look at the chip identification on the chip itself. This one says FTDI 232RL, which is very difficult to see on camera, but with a magnifier I can see it. I will be using a program called KiCAD. KiCAD is a free electronics design software that allows you to create schematics and PCB layouts, with the added feature that you can see all of your layouts in 3D as well. I used to use a program called Eagle, but Autodesk has bought them and started a subscription model. But if you're starting out, I think this is a better approach using KiCAD, and if you need to get into a more professional suite, Altium software is probably a better choice because you can make better decisions on trace design and overall better circuits to minimize noise, crosstalk, impedance on traces, things like that. So to get started, I'm going to click on the download button and install it for Windows because that's what I'm working on. And I'll just start with the first link it shows me. Once you've downloaded the program, I'm going to double click the application to install it and go through the standard installation procedure. And it gives you the option to install FreeCAD. I'm going to go ahead and do that. I don't think I've ever used FreeCAD before. When you start KiCAD for the first time, it's going to ask you to either start with the default settings or if you have settings from a previous version. I'm going to keep it with the default and press OK. So I'm going to go ahead and start with a brand new project, and I'm going to call this FTDI 232RL USART. Now it's going to create two files for you. One is the PCB and the other one is the schematic. So I'm going to double click the schematic and I'm going to go with the default option they have here. If you have a symbol library that you use, you can go ahead and make the change. Okay, so we have our blank editor here, and you can see that there is a title block and a border and a space for you to apply your schematic. I also want to mention that another excellent resource is Phil's Lab on YouTube. He goes into great depth on KiCAD, overall schematic and circuit design, and PCB layout. And also he goes in depth in proper trace application on the PCB. So make sure to check out his channel, and if you found him through me, make sure that you mention that in his comments. So the first thing we need to do is put in the chip that we're using. We're going to use the add a symbol. I'm going to press OK for the default, and we're using the STM32 F0. So we have the F030 R8 is the one that we're using. So I'm going to go ahead and select that, press OK, and it's going to provide you with the symbol for that microcontroller. You can see that it has all of the pins that we're familiar with. You have the VDD, which is the positive DC voltage, and then you have the VSS, which is the negative DC voltage. The first thing we want to do is apply our decoupling capacitors that we already have on all of the projects that we do. So these are the decoupling capacitors I'm talking about. The one that is very close to the main power, the ones over here, the one over here at this location, and the one over here that is next to this power pin. To add the decoupling capacitor, go to the symbol and type in C. and you're going to find that capacitors, general capacitors, are just represented by the letter C. Press OK. And I'm going to put a few of them here. On the prototyping environment, I have 3 of them. So I'm going to put in 3, but I want to add another one to the analog power pin. So I'm just doing a copying and pasting using the Control C and Control V. So now I have 4 of them. Now I want to add power to the chip itself. So I'm going to go to the little earth ground symbol here, and it's called Add Power. So I'm going to click on that, and I'm going to type in the 3.3 volts, and a standard 3.3 volts will be fine. So I'm just going to put that over here because I'm eventually going to connect all of this together to the VDDs. And on the VSS, I'm going to click on the power again and type in the ground for a ground symbol. So I'm going to place that around here, and now I need to connect the nets, which are the wires or connections between the various symbols to their pins. So I'm going to start with the positive pins. The net or wire command is right here. So I'm just going to click on the little circle. That would be the origin for the symbol. Going to connect them together. I'm going to do the same thing with all of these, because all of these decoupling capacitors are going to connect to the positive 3.3 volts, and it's also going to connect to the ground. I'm going to connect all these together because that's the way we have it on the prototyping environment. They all need to go to positive, and then I'm going to go to positive here. These all need to connect to ground, but I also need to connect the VSSs to ground. So I'm just going to go ahead and connect all these together, and then I'm going to place a ground symbol. I could just copy the ground that I have here, but it's already in the recently used, so I'm just going to press OK, and I will wire it up using Add a Wire command. I know a bunch of you want to go straight to the comments because of what I just did here. I put the analog positive DC voltage and connected it with the rest of the DC voltage, and I wouldn't be doing this if I was going to be using the analog to digital converter. The reason why I'm connecting them all together is because that's the way I have it on the current circuit, and I'm using the analog power pin because I need to use that for adjusting the clock to 48 megahertz. Most of you that have watched the series know that I needed to connect this pin to enable a certain feature of the clock, and if I didn't do this, I would render the microcontroller useless until I did a full erase on the microcontroller. As you can see in the datasheet for the STM32 F030, you'll notice that the VDDA, the analog positive voltage, controls the PLL, which is the clock multiplier that I was using for bringing the clock speed up to 48 megahertz. If I was going to use the analog to digital converter, I would put this on its own supply and follow the recommendations of any application notes for the STM32. But for now, we're going to leave it like this because that's the way we're using the microcontroller in this part of the series, and you'll see any changes later on when we start using the analog to digital converter. Let's go ahead and add some numbers to these capacitors and also some values. The values for the capacitors are 100 nanofarad or 0.1 microfarad. To change the value, make sure that you're in the pointer select item mode and just double click on the value, which is the C underneath the name or identification designator. So I'm going to put the value as 100 nanofarad. I'm going to do the same thing to all of these. And now I want to number or name these capacitors. And I'm just going to go in and number them myself. You can have this automatically done, but I think it makes more sense to number them manually. So it makes more sense when you're identifying these components on the PCB. We also want to do it to our main component, the STM32. Just say U1. And now that we have fully identified and added values to our components, and I'm going to do something a little bit unconventional here. I'm going to go into the PCB board editor at this point because sometimes it makes sense to go back and forth as you're putting in the schematic. Some will create the full schematic and go to the board editor at the very end. But I want to do this in a more unconventional way where I'm placing components in a PCB as I make the schematic. And the reason why I'm doing this is because placement with a lot of these components is critical in most respects. We know that the decoupling capacitors need to be close to the microcontroller, so I want to make sure that I do this first. When you create a PCB for manufacture, you want to make sure that these decoupling capacitors are really close to the microcontroller. I'll go into much more detail on decoupling capacitors in a previous video, and I'll leave a link in the description. Still one more thing we need to do before we go into the PCB board editor. Anytime that you create a new symbol, you need to create a footprint for it, because these are generic symbols and there are literally thousands of footprints that you could apply, depending if it's through hole or if it's SMD, and the dimensions of these footprints. Footprints get larger when their power ratings are higher, so you want to make sure that you have the appropriate footprint for the symbol that you're creating. The way to do this is to run the footprint assignment tool. So let's go ahead and do that. You'll notice that it shows which footprint that it needs to assign in the schematic with the capacitor selected in the Assign Footprints dialog box. You'll notice if I select another one, you'll see the other capacitor highlight, and when I highlight the main microcontroller, it will focus the symbol on the schematic editor for that selection. So let's go back to the first one. So we need to assign a footprint for our decoupling capacitors. So I am selecting the filter footprint list by pin count. We're going to have 2 pins or 2 pads on these capacitors. And I'm also selecting the filter footprint list by footprint filters defined in the symbol. If you're going to be making the footprints for SMD, which I suggest doing because this is the easiest way to have the boards assembled by a manufacturer, or if you're doing it by yourself and soldering them by yourself, you'll want to choose the component that is economical for the production size or what you might have on hand. In my case, I have the 0805s on hand because I use this quite a bit in my other projects and circuits that I sell. And it's also a lot easier to hand solder if you need to. You can select whatever size that you want. The 0402s are fine for manufacturing, but it's probably a little bit difficult to hand solder these. For me, I like to have that option if I need to hand solder them. If I find that manufacturing them overseas is more expensive than me doing it by hand or me hiring somebody to do it, I like to have that option. So I'm going to go ahead and select the 0805, and I'm going to select the hand solder version. I'm just going to double click the selection. It automatically goes to the next one. So I'm going to go ahead and do the same thing. And this package is the QFP or the LQFP64, and that's standard for this particular microcontroller. I'm going to press OK. I can go ahead and go into the PCB board editor now. I'm going to go ahead and click on the icon that says Update PCB with changes made to schematic, and you'll see that it has all of the components that we have in the schematic. It also contains the footprints for all of the symbols, and it shows that there are no warnings or errors. So you can go ahead and press Update PCB and close, and it gives you the ability to place it anywhere on this sheet. So I'm going to go ahead and zoom in, and you'll see how large those 0805s are. And I'm just going to place these footprints where I think they should be placed. And I'm using the M command or move, and I'm going to rotate it. You can use the R command to rotate. So I'll be doing that as I move them. And you can also change the grid spacing. This grid spacing is quite large, so I might want to do that. But I just want to get these into the general locations. So I'm going to put this one next to this pad. I'm going to move this one. Put this one next to this pad. General locations are fine because you can refine these locations later on. And the last one is located right around here. So I'm just going to put it somewhere in this location. So these are general locations. I'm going to want to change the grid spacing so I can get them closer, but I don't have to worry about that yet. This is just to kind of define where generally these capacitors are going to be placed. So now we have to give this PCB the ability to receive power and to be able to program the microcontroller. Currently, the ST-Link is providing the power that we need, and we can connect to 3.3 volts or 5 volts with this ST-Link. But in your PCB, you may want to provide power in another way. You can even provide power using the FTDI board, using pins on the side. So you have some options, and we'll delve into that a little bit more when we look at the schematic for the FTDI. The manufacturer of the integrated circuit that you want to implement into your project will typically have an application circuit in their datasheet. So I'm going to look up the datasheet. The FTDI chip is the FT232RL, and just by putting the word datasheet after it, you should be able to find the datasheet. So I'm going to go ahead and click here for the datasheet, which is right at the ftdichip.com, the manufacturer's website. And you'll get a lot of information about the chip, and you'll want to read this information so you can find out any specifications that they require or that is required for that particular integrated circuit. This data sheet has many application examples: USB to RS-232, USB to RS-485, USB to RS-422, and USB to MCU, which is microcontroller UART interface, also an LED interface, and using the external oscillator. We're going to be specifically interested in the USB to MCU UART interface because we don't need to have a connection to the computer or to an RS-232, which is a plus and minus 9 volt shift leveling connection, nor do we want any of the RS-485 or RS-422 connection types. So let's go ahead and go straight to the USB to MCU UART interface. This is the USB connector, and you have the USB DM and DP pair, a positive voltage and a negative voltage, and a ground, which is decoupled with a 10 nanofarad capacitor. This integrated circuit actually has an internal voltage regulator because it can provide you 3.3 volts out on this pin here, and it can also provide you the 5 volts, which is typically connected to the USB through the VCC. So we have a couple of options. And you can see here, this is the connection between the FT232R and the microcontroller. So you have the lines, the RXD going to the TXD, which is the receive. It's connected to the transmit from the microcontroller. The transmit from the FT232R is connected to the receive from the microcontroller. The ready to send and the clear to send is also connected to the microcontroller with those pins, if you need to use those pins. There's also a convenient 12 megahertz clock that can be used with the microcontroller, and the CBus 3 pin can be connected to an IO pin of the microcontroller, so the microcontroller can wake up the integrated circuit from a suspend mode. But those are optional, so we don't actually need to worry about these two connections. You can see that there is some information below the diagram that can provide some extra information if you need it. With the LED interface, if you want to show some indication of transmit and receive, you can also implement this schematic as well. Before you use this integrated circuit in the schematic, you want to make sure that you understand the function of each pin on the integrated circuit. There will probably be some very important information on each of these pins that you will need to know. Otherwise, you risk that part of the schematic not working. One such example on needing to understand each pin is there may be a requirement that it has to be either pulled up, connected to ground, or can be left unconnected. The test pin must be tied to ground for normal operation, so we have to make sure that when looking at the application circuit, the test, we have to confirm that it's tied to ground, and in this case it is. So the application circuit is actually giving you the condition which it requires to have normal operation. But you can see that these pins don't have anything, they're just floating. So you want to make sure that if it's not going to be connected, that it doesn't require being connected to ground or connected to VCC. You'll also see options on how the integrated circuit is powered. So you can have it powered by the USB bus. So let's take a look at the USB bus powered configuration. And you can see that the VCC is going straight to the VCC here from pin 1, and pin 4, which is ground, is also connecting to the grounds here. The self-powered configuration, you can see that there's a cut in the line here. The USB is pulled down to ground using a voltage divider to the reset. And the chip is powered by another source between 4 volts and 5.25 volts, which is the band that this integrated circuit will operate. USB bus powered with power switching configuration, where you can use the VCC from the USB port, or you can use a external power supply switched on with a MOSFET, where the 5 volt power is sensed into the gate of the MOSFET. It will use the external power supply. And finally, the USB bus powered with selectable external logic supply, which uses a jumper to select the supply for this integrated circuit. We will be using the USB bus powered configuration, as this will give us the option of using 5 volts or the 3.3 volts for the microcontroller. I'll start by adding the FT232 chip. So let's go back to the schematic, and I'm going to zoom out here a little bit. Click on the symbol and type in FT232. And the RL is right here, so we can just bring this right on in. I'm going to try to find an open area here so I can add the components it needs. I want to keep the circuits logically separated, so the schematic diagram is organized and easy to read. I'm going to move this a little bit. I'm just selecting with the select items icon and using the M to move. That's pretty good. I'm going to go ahead and add this 100 nanofarad, which is something I already have on the schematic, and all the ground connections. Test A ground GNDs and the 3.3 volt out. Okay, let's put the grounds on the grounds. We could go to the power, or I can go over here and steal this one. I'm just using the Control C and Control V. Now let's wire it up. Okay, so we still have that test, so we're going to go ahead and wire up the test to ground as well. Okay, so we need a decoupling capacitor on the 3.3 volts. Where is that 3.3 volts? Okay, here it is. We already have a decoupling capacitor here, so we'll steal this one. Since this is already a 3.3 volts, I'm going to go ahead and put a ground here on the decoupling capacitor, and I'm going to go ahead and wire up the 3.3 volts to the decoupling capacitor. But I have to figure out if I'm going to use this 3.3 volts out or the one on the ST-Link, because we have two places that will provide the 3.3 volts. In the USB to microcontroller interface, you can see that the microcontroller is using the VCC as its power, but this is 5 volts. So I want to use the 3.3 volts coming from the USB, which is going to be essentially from the FTDI chip if the microcontroller is not plugged in to the ST-Link. So I can bring this up to the 3.3 volts on the circuit, so the microcontroller can take advantage of this 3.3 volts out, or it can take advantage of the ST-Link if it's plugged in. In a lot of cases, they won't be plugged in both at the same time, because if you're using the microcontroller and the FTDI chip just to do communication and the firmware is already on the microcontroller, there's no need to have the ST-Link plugged in anymore. So I'm going to go ahead and put the power symbol on the 3.3 volts out on the schematic, and which is this. So it's going to tie it all together. Okay, so let's go ahead and wire that up. So now we have the 3.3 volts out wired with the 3.3 volts as a common voltage for the microcontroller if I'm not using an ST-Link. Let's see what else we need to put in. We can wire up the RX receive to the transmit of the microcontroller, and then the transmit of the FTDI to the receive of the microcontroller. Let's go ahead and do that. We could just put a wire directly from the receive to the transmit of the microcontroller, or we can just create a wire and then name the net on both sides. So let's do that as a way to wire without having to wire from one device to the other. It keeps it a little bit neater that way. Now we need to figure out which pin is the transmit. So I'll go to newbiehack.com to find that out. In our circuit, we were using the receive and transmit here. So that's pin number 42, or PA9 for transmit. So PA9 is right here. So let's go ahead and wire this up. So these two wires are now the same wire. Just to prove this, let's go ahead and go to the PCB board editor and see if the receive is actually physically connected with the rat's nest to the PA9. But before we go into the PCB, we need to correctly annotate this. So this one would be 5, I think. Yeah. We need to create a footprint for this, so let's go ahead and do that. Oh no, I already have that because I copied this from that area, so I don't actually need a footprint. So let's go ahead and go into the PCB. I'm going to update, and I forgot to annotate the U, but I'm going to go ahead and automatically annotate it. All right, so I'm just going to drop this somewhere in the vicinity. Looks like this would be probably the best place here, because the connection from the receive to the transmit is on this side of the chip, so it'll be a little easier to wire up traces. So this should be the PA9, and this is the receive. Yeah, the FT receive, which is what I named it, is connected to this one, which is 42 FT receive. Let's go back to the schematic. So adding these labels are a really convenient way to keep everything organized so you don't have nets or wiring all over the schematic, running all over each other. So let's go ahead and connect the transmit to the receive, the transmit of the FTDI chip. I'm going to go ahead and wire this and then add a label, FT transmit. All right, so now I want to put that on, where was that? Let's see. So we're going to put that onto the receive pin on the microcontroller, and that's PA10. So PA10 right over here. And I'm going to just copy this and paste it over here. So now I have the FT transmit going to the receive pin of the microcontroller, and we can go ahead and confirm that was implemented on the PCB. So update. So now we can see that the FT transmit, which is pin 1, is going to pin number 43, which is number 43 on here. So that is correct. While we're here, let's go ahead and move this one, and I can rotate it so we don't have any overlapping rat's nest on this. And we want this one as close to this chip as possible so we don't have any transients or noise on these traces. So let's go ahead and go back to the schematic and continue with the application. So we don't really need any of the ready to send or clear to send connections, and we don't need the use of the 12 megahertz clock because that's not the way we have it currently on our circuit. So I'm going to keep those off. So it looks like the VCC over here is being decoupled as well with 2 different types of capacitors. So we'll go ahead and implement that. There is a 4.7 microfarad capacitor and a 100 nanofarad capacitor. So let's go ahead and put those in. I'm going to put in a polarized capacitor for the 4.7. I'll put this one up here and I will name that C6, and this will be a 4.7 microfarad. Then I'm going to go ahead and use another one of these here. On this application, we have the ground going to the bottom of these 2 capacitors and the VCC, which is the 5 volts from the USB. We haven't implemented the USB yet, so let's go ahead and do that first before we wire this up since we need the VCC. Before I put the USB connector in the schematic, I want to take a look at what was being used on the FTDI board. This one is the mini connector, so I'll just go ahead and pick a mini. It doesn't really matter which one I pick, mini or micro. I have both cables and a multitude of each, but I'll stay consistent and I'll use the mini. Now we know what type of USB connector to use. Let's go ahead and look that up. So we have mini here, press OK, and then we'll just put it somewhere around here, which is close to these capacitors. Before we get to the capacitors with this V-bus, we need to add a ferrite bead. A ferrite bead prevents electromagnetic interference and also high frequency noise. So we can put this in line with the V-bus. So let's take a look at the symbols and add the ferrite bead. I'm going to select the ferrite bead small and use the R to rotate so I can put it in line here. Now all we need to do is wire it up, and this is going to go to ground on the bottom here. Let's steal this ground on the bottom. I don't think I'm going to use the 5 volts from the USB for the microcontroller side, but I have to connect it to the FTDI chip, as can be seen on the application circuit. So I could just directly connect it to the VCC and the VCC IO. So let's go ahead and do that. So the 2 are here, so I'm just going to connect those together and add another power symbol, and I'm just going to add that here as well. I'm just going to copy and paste it to this location. So now those 2 are connected. Let's see what else I need to do here. I've got this part. Oh, I need to connect the data plus and minus pair. It looks like it doesn't go all the way to the 3, but I think that's a printing error or an error in the PDF. So I'm just going to go ahead and connect those 2 together. So I'll just use the same labeling technique I did with the transmit and receive. So I'll do D plus and I'll do D minus here. And I'll go ahead and copy and paste that to the D plus and D minus over here. I'm using the R to rotate it. So now we have the D plus and D minus connected to the D plus and D minus of the USB connector. And I'm going to go ahead and connect ground to the ground for the USB connector. And I'm also going to connect the shield to ground. In the application circuit, it doesn't have the shield going to anything. It doesn't have the shield going to ground. It is left unconnected. But there's a lot of metal here, so I don't want this metal to be an antenna. I mean, I'm already using a ferrite bead, so it's already going to be reducing the noise, but it doesn't hurt to put the ground on the shield. To determine the ferrite bead that we need to use at this location, general guidelines state that you need to determine the ferrite bead size according to the current that's being drawn on the circuit. But you can also go to application notes by the manufacturer of the integrated circuit, in this case FTDI. And they have a document called USB Hardware Design Guidelines for the FTDI ICs. So let's take a look at the table of contents. You can see that ferrite bead use and placement, USB peripheral devices. So let's go ahead and take a look at that. And it recommends that the USB power signal should have a ferrite bead in series with the V-bus, which is the VCC. it does not recommend that it be used in the DP and DM signals, which is the data plus and minus. But I did notice something different with the application note, and it adds a 10 nanofarad capacitor, which does further filtering. And they're using an 0603 ferrite bead with a value of 330. As long as we use the pad of 0603, we can place a ferrite bead at that location, and we can change the ferrite bead if we need to, but we will label it according to this application note here. It also recommends that the capacitor and the ferrite bead be placed as close to the USB connector as possible, so we'll do that as well. So I'm going to just select this and copy it so I can use that as a label. And I know it's going to be a 0603, so I can state that with the footprint. And the FB will be number 1. It's the only one we'll have. This will be the only J we have, so we can put J1 there. And we need to determine a footprint for that, so looks like there's some I did not annotate, so I'm going to go ahead and allow it to do it by itself. Looks like it was this one here. Alright, so the 4.7 microfarad capacitor, I need to create a footprint, and the ferrite bead. Let's do the ferrite bead first because we know that's an 0603. The USB Mini. If you need to look at what the footprint looks like, because the USB Mini has many footprints to select from, you can click on this button right here and it will show you a view of that footprint. Let's take a look at that. Alright, so we can just select from the right and just scroll down until you see the one that you have access to or you can use in your circuit. This is the footprint they're using for the USB. The footprint that resembles the one on the FTDI board looks like this one. So I'll just use this one. But in general, you'll want to look for the component that makes more economical sense if this is a large production, or makes sense with the way you want the board to be designed. You can see the capacitor they're using is right here. This is the 4.7 microfarad capacitor. They're using an 0805 capacitor, and all of these look like the standard can looking capacitor. So I may have to change the schematic symbol, but just as a placeholder, I'm just gonna put in the smallest one here because I could probably use this also as a SMD component set of pads. I'm going to go ahead and press OK and go to the board and update the PCB. For this, I'm just going to put this aside. Looks like it's going to want to be on this side anyway of this chip because you can see that the data lines, the data pair is over here. You'll also notice that the capacitor symbol is not that much larger than the 0805, so I can use that if I wanted to use an 0805 component. Now I need to add the connector that will allow me to program the microcontroller and add power via the ST-Link. So let's go into the symbols, and it's going to be a connector. And I'm going to use a 4-pin connector, male. So I'll just put that somewhere in the vicinity of SWDIO and the SWCLK. I've got to find out where that is. So I'm going to go back to Newbie Hack and find that out. Alright, the SWDIO is number 46, which is PA13, and the SWCLK is pin number 49, which is PA14. So PA13 and PA14. So that's on this side here, so I'm just going to move it to here. Not that it really needs to be that close, but it makes it easier for me to put it into the schematic this way. I'm going to move this down so it's not crammed into the space. And the J, we need to number that, but I'll have it automatically number. The next thing I need to figure out is which pin should I have going to the 13 and 14. It doesn't really matter because the SWCLK and the SWDIO and the 3.3 volts and the ground, they're all individual pins. So I can pretty much make it any one I want, but I do want to make sure that it is labeled on the PCB. Oh, this is in the wrong direction, so let's rotate this around. So now wiring it up. PA13 and PA14, I'll put those to the center. And I'm going to name these. The PA13 is the SWDIO, I think. And PA14 was the SWCLK, but I'm going to confirm that. 13 is SWDIO. Okay, yep, I got that right. Okay, so I think this is the second J. I changed this connector to a J2. Now let's add the footprint to this connector. Run footprint assignment tool. And I need one that is 2.54 millimeters spacing or 0.1 inches spacing. And I want to look at the footprints as I browse them here. So let's see here. It looks like something like this. This is a 2.54. Anything that has a 2.54 will work. So this one is 2.54, but it's a surface mount version, so it would be able to be easily assembled by an assembly house or a PCB provider. Or you can use something like this and hand solder it. I personally like these. It can still be assembled by a PCB manufacturer, but it gives also you the ability to do it by hand if you want to. I'm gonna go ahead and put that in there. So I'm just gonna steal a 3.3 volt and a ground from somewhere. Control C, Control V, and I'll just connect it to that. And then Control C, Control V. I need to select it. All right, and then just move it there, but I don't like it hitting this, so I'm going to move it over here and then just wire it up. I like to keep the power symbols in the direction, like the positive power is always pointing up, ground is always pointing down. Okay, that works. Now I need to add the mounting holes that's going to be used in the PCB, but you do this in the schematic. I'm going to add the mounting holes. I'll put it on this side here, and that's the symbol. The mounting hole here, and I'm going to create 4 of them because that's generally what most boards have, but you can determine how many mounting holes you need for the case that you're creating. So I'm just going to copy and paste this, and I'll have these automatically assigned. So run footprint assignment tool, and these mounting holes are going to have different dimensions because you will need to purchase the hardware to use for this. So you have to specify the mounting hole on the size of the hardware that you're going to be using. I'd probably use like an M3 or M4 screw. So if you wanted to use, say, an M3, you'd probably want to have something a little bit larger than a 3mm hole. So I can go with maybe a 3.5mm. Same thing with these, and press OK. Okay, we've made a number of changes to the schematic, so let's go ahead and update the PCB with the changes to the schematic. Got 0 errors and 0 warnings. Go ahead and update. You'll see that the new mounting holes are present and the new connector is present. I'm going to put these on the left-hand side for now. Now that I have everything on the PCB, I need to move everything in place. I'm keeping the components that are meant to be next to each component together, like the microcontroller with the bypass capacitors, the FTDI with its bypass capacitors, and the USB connector with its capacitors. So at this point, I'm just going to move things around to make sure that the air wires are not crossing over each other as much. And I can select a number of components together to do this. But I'm going to go into this one first because I've already worked with the microcontroller, getting the capacitors arranged, and the FTDI chip with this capacitor. But I haven't really worked with this one yet, just to make sure that these capacitors are on the correct side of this connector. So I'm going to move all of them a little bit farther away. Then I'm just going to start picking things up and moving them. So this one wants to be connected to this particular pin, so I'm going to go somewhere around here. Maybe I'll rotate it and put it in this area here. And while I'm moving things around, there's a purple outline that's called the courtyard. You want to make sure that that courtyard is clear of other courtyards, of other components. The courtyard is a good way to make sure you have enough space between components so they don't interfere when the assembly takes place. So let's see where this wants to go. This doesn't really need a specific area, but I'm going to keep it close anyway. And same with this one. So I'm going to put these near each other here. This is at the edge of the board over here, so I want to make sure that I don't put anything farther than this area right here where the grounds are. I'll probably put this here for now. I'm just going to take all of it. I'm going to rotate it because I want these pins to be closer to the FTDI chip. It wants to be kind of like around here somewhere, but I know when I do the overall board organization, I have the mounting holes to work into the arrangement, and I want the board to be somewhat rectangular or square in shape, so I want the components to be somewhat organized in that form. Now I can move the connector where it needs to be, and it looks like it wants to be close to these 2 pins here, the SWCLK and the SWDIO, which is right over here. But I'm probably going to put it kind of on the top of the PCB here. I'm going to rotate it. Now I'm going to move the holes. I'm going to move it somewhere in this location. And when I press move again, when I lay it down and then I press move again, you'll see the crosshairs. And you can see that it doesn't align up with the mounting hole above. But at this point, I don't really want it to because I may be moving things around. But I could use that as a way to align them so that they're always going to be next to each other and arranged in a pattern that makes sense. Looks like I want to probably move some of this stuff around because it's going a little bit too far this way. Or what I could do is I can move these mounting holes over here. They don't have to be right at the edge of the board. Okay, that's good. That one needs to go down a little bit. Okay, so those are all placed in a pretty good location. I can probably move these holes to the right a little bit. I still think I want to move these around a little bit, so I'm going to move the FTDI chip and move it a little bit closer to the microcontroller and do the same thing with these. And I also want to move the bypass capacitors a little closer. I can probably change my grid a little bit tighter, but I think this is fine. I can always adjust as I'm doing the routing. You don't want to go too close that you can't route certain signals. And I might want to move this one just a little bit up because the data pair is going to need to go around the capacitor. We're going to get a little bit closer with the connector. And I'm going to keep the ferrite bead over here. I may have the components a little bit too close to each other, so might have to move them. Before I go any further, I want to talk about the layers a little bit. These are the layers you have for the PCB. The first two is the copper layers. The FCU is the top layer or the front layer, and the B is the back or bottom copper layer. If I use this convenient drop down, you can use the only show the copper layer, and what it'll do is it'll turn off or hide all of the layers except for the two copper and the edge cuts. And the reason why this drop down is so convenient is because when I start doing the routing, I'm only going to want the copper layers to be shown. And when I'm finished, I'm going to want to look at the front layers, and I can get everything arranged like the silk screen. And then I can look at the back layers to make sure the silk screen is good with that as well. I'm just going to show all copper layers, and then I'm going to turn the copper layers off and show you each layer one at a time. You can see the air wires are still shown. So the top copper layer or the front copper layer is only the copper that's shown on the top. Adhesive layer, USB connector has two adhesive locations because that connector will get some abuse over time with the constant plugging in and unplugging of cables into that particular connector. So it needs some mechanical support to be able to make that connector robust. The paste layer is where only solder paste will be applied. And this is the layer that PCB manufacturers will create a stencil so the paste can be applied using the stencil. And it's also important to understand the thickness of a stencil because of the aperture sizes for a microcontroller like this. The apertures are really small and you don't want to get too much paste on there, so you want a very thin solder paste stencil. Because if you have a thick solder paste stencil for like pads like this, then you risk the possibility of pins bridging when they're being reflowed or the solder is being melted. The silkscreen layer is the layer that is actually being painted on with some kind of ink using a silkscreen, and it is applied on top of the PCB so you can understand what component goes where and also any version markings and logos or anything else you want to show on the board. The solder mask will show where solder will be laid down. When you're soldering, you want all the spaces between the solder to be free of solder. So the solder mask is a coating that is applied that resists solder, so you minimize the bridging of two pins. The edge cut is a really important one because that shows the limits or where the board is going to be cut by the PCB manufacturer. If you look at what the board's going to look like before you put those edge cuts, it's just going to create its own edge cuts around the boundaries of where all of the components are arranged. So when we create our own edge cuts, it will change where it thinks the boundaries need to be. The courtyards are boundaries around the components that you don't want to be overlapping from component to component, because the assembly of the PCB, the components being applied, will be difficult, if not impossible, if these courtyards are overlapped. The fabrication, the layer F fab, is where the PCB manufacturer will use for assembly. so it tells them what component goes where, but it doesn't show up on the actual PCB. So you won't actually see this information. This is only for the assembly to take place, but you can move these descriptions or identifiers around. For instance, if I just click on the mounting hole and use the M key, you can move this anywhere you want, so it makes it easier to see. All right, now we have a pretty good grasp of what all of the layers mean. I'm going to go ahead and take a look at the top copper layers, and I'm going to create the edge cuts. I also want to put the courtyard on there because I want to make sure that I am not going to create an edge cut that is too far inside. Like for the mounting hole, I want some area for the hardware or the screw to provide a sufficient mechanical hold on the board. So I'm going to go ahead and start creating my edge cuts, and I'm going to use the draw line tool to do this. And I'm going to draw them using the courtyards as my guide. You want to make sure you're in the edge cuts layer when you're applying this geometry. And I kind of want to have my last line somewhere around here. I don't want to get too close to the ground, but it might allow me to do that. Let's see. If I go into my select mode, I can select this and I can just drag this around anywhere I want. So I can connect these two together, and I'm just clicking and dragging. I could round over these back edges because it would probably look a lot better if I did that. So now we can take a look at the 3D viewer to see what we have. And you'll see the new cuts. You can see that the connector now is overlapping the edge here. So this, I'm pretty happy with the edge cuts, but I want to show you one thing you can do to make the corners look a little bit nicer. I'm going to create an arc. So what I'm going to draw is a circle from the center of this, and I'm going to go clockwise. So start here and then end here. Do the same thing here. Start here and then end here. So I have these two arcs here that I want to use as the edge. I'm going to go back to the select items, and I'm just going to select these, and it's going to snap to endpoints of the arcs. So that might look a little bit better. Let's take a look at the 3D view of the board. That looks kind of nice. I kind of want this to be a nice filleted corner as well. It's not going to be right next to the hole, although I could move the hole closer to the edge. I might as well do that because I have the space. You can also click and drag to move instead of using the M key. Now, there is a way to just use these existing arcs and just copy them and paste them here. I think creating the arc is actually a little bit easier, but I'll show you how to do that. I'm just going to do a Control C and then Control V. I'm going to move it here and then just press R until it becomes located in the correct place. I do the same thing, Control V, and then R when I get it to the center of that hole. Done. Now I'm going to just do the same thing. Just move these ends to the endpoints of the arc. There. So let's take a look at the 3D view again. Now you can see that all the edges have a fillet. The PCB manufacturer won't have a problem creating these fillets at the corner. If you have an edge cut, let's say, like if you have a board that looks kind of like this, where it has an inside corner, a PCB manufacturer will not be able to create that inside corner with a perfect 90-degree inside corner. But they can create a perfect outside corner, because when they're cutting this out, they're using tooling that has a diameter. And when that tooling goes around the outside corner, it can create a perfect outside corner, but the inside corner is always going to have a little bit of a fillet because of their tooling. All right, now I'm going to go ahead and start routing it. I may find that I need more space in here, so I can always work on that as I route it. And I'm going to keep these layers on except for the courtyard, and I want to make sure that I'm on my top copper layer. There's one thing of preparation that I want to do first, and that is I want to set up some trace widths for use with power and signal. But I also want to make sure that the bottom copper layer is a power plane. I've already changed this before. The power plane is going to be a ground plane or a ground pour. Where I'm going to set up my widths is in the predefined sizes. These widths are going to show in this drop-down menu right over here. So whatever you put in this location, you'll see in this drop-down menu. I've already put 0.5 in here. This is going to be used for my low power traces. Since USB is not recommended to go over 100 milliamps, 0.5 millimeter is going to be fine. And the signal traces can be a lot smaller than that. And I'm going to use the default that KiCAD has for the standard traces. So I'm only going to have the 0.5 millimeter as an option. If I don't use the 0.5 millimeter, I'm just going to use the default. You do want to use traces and rules that your PCB manufacturer will be able to manufacture or fabricate. That's generally going to be on the physical stack up, where you have the silk screen, paste, solder mask, copper layers, dielectric within the parameters and constraints that the PCB manufacturer can handle. The dielectric specifically is the thickness of the board separating the layers. And in this board, we're just going to have two layers, which is the top and the bottom. And the thickness of that board is 1.6 millimeters. This is a default, and it is of the FR4 material. The thickness of the top copper layer is going to be 0.035 millimeters. And if you need increased power and possibly increased thermal efficiency, you might want to have a thicker layer for copper on the bottom and top, depending on how you determine your power requirements. The top solder mask is going to be 0.01 millimeters, and the bottom copper is going to be the same as the top, and the solder mask on the bottom, which is the same as the top. In the design rules with constraints, you want to take a look at all of the constraints, and the constraints are generally minimums for clearance, track widths, and diameters and things like that. So you want to look at all of these values and make sure that the PCB manufacturer will be able to manufacture the PCB with these values, and also that your signals and power will function effectively with those numbers. These are the defaults, and I'm keeping them as the defaults. You can also specify net classes. I'm not going to do that in this particular video, since this really isn't a complex board and I don't really need to determine net classes. But if I had a lot of different signals and powers and things like that, I would probably set up the net classes. Okay, so let's go back to routing. I'm going to start off by creating a bottom layer ground plane. And to do that, I'm going to have to use the add a filled zone icon to start this process. And I'm just going to arbitrarily create a beginning area that is outside of the PCB on one of the corners. And then I'm going to specify what it is, and this is going to be ground. So I'm going to press OK and then start drawing it. And it doesn't really matter how you draw it. It would matter if you are needing to separate your grounds or creating a specific shape because of, say, if you're using the analog to digital converter, because that would require its own defined ground plane that has a very small section that is connected to the larger ground plane. But in this case, we're not using the analog to digital converter, so I'm just creating some boundary around it. And once you press B to flood the PCB, you'll see that it only goes where it needs to go, and it doesn't go outside of the edge cuts, and it respects the clearance from the pads specified in the preferences. And you'll also see anything that has ground that is a through hole will be connected to that ground already, so you won't need to route that portion of the PCB. Now, it might look a little bit hard to read with the ground plane visible, so I'm going to hide the ground plane. I'm going to make sure that I'm in the front copper layer so I can start drawing, and I'm going to go ahead and start drawing the copper. And I'm going to use this icon called route tracks to do that. I'll start off by drawing the signal wires, and I'm just going to hover over the pad that I need to start from and then the destination, and I'll go to the destination. And you'll see that as you move the cursor around, it'll only route the track where it can route the track, where it's able to route the track. And I like the tracks to leave and enter the pads from the end of the pad and being symmetrical. And I also want to try to keep the traces as far as possible from other traces to limit crosstalk. I'm also going to reduce the grid spacing to a 0.01. Be a little bit easier to manage the location of these traces. And I clicked on the center of this because I want to make sure that it adjusts itself. You can see that it moves up a little bit when I get close to the center of this pad. So I did the FT receive and FT transmit. I'm going to go ahead and do a data pair for the USB. And I'm going to be going through a lot of these air wires, which is going to be a little bit difficult to trace for these other ones like the VCC here. I want the signal lines to have the most efficient routing. That may be a little bit too close. So I'll do this. All right, and now the D here. This one I might want to go underneath this one. I could go around the back and then come up. But then what I'm doing is I'm changing the length of this trace compared to the length of the trace next to it, which is a data pair, and I want to try to maintain as close to a length as possible. I can use the true length of a single track feature to increase the length of the shorter one. if I want to do that. So I'm going to go around the back here. I'm going to delete these two. Might be a little easier to rewire that. So if you wanted to increase the length of this trace here to more closely match the length of this trace, you can use the true length of a single track and do something like this to increase that length. But since these are so short, it doesn't really matter, and this is a very simple circuit. I'm going to undo that. I'll go and do the SWCLK next. And now I think I'm done with the signal wires. I'm going to go ahead and start to wire up the 3.3 volts and the VCC. For the larger capacitor and the ferrite bead, I want to have a larger trace width. And I'm going to do this also with the ground. So I'm going to go over here and change my track width to 0.5 millimeters. And I'll start tracing out the VCC. And I'll do the 3.3 volt, but I'm going to do that in the standard default track width, like I did the other ones. I think I'm left to the ground now. So with the grounds, I want to provide vias to the bottom layer for most of the grounds, unless they're a really short connection to another ground. But even though it's a short connection, I'm still going to want to take one of those grounds to the bottom layer. So I'm going to go ahead and show that right here, but I'm going to change my track width to 0.5. I'm going to want to I want to connect this ground to the bottom layer using a via. So I'm going to use the tracks, but I want to turn on my bottom layer just so I know what I'm doing. I'm going to go ahead and do a trace, and I'm going to press the V to add a via and then click. And then I'm just going to escape, and you can see that it's connected to ground at that location. You can see that if the trace is too large for the ground pad on an IC or the microcontroller, it won't allow you to draw it because it will conflict with pads. It'll conflict with the neighboring pads. So I have to go back to the default that I'm using. I'm going to go ahead and connect up these VCC since I'm in the correct width. I'm able to connect a trace to another trace if I hover over that trace. They're going to be the same net anyway, so that'll be a convenience. And in this case, I think I'm going to have to go underneath, but I'm going to try to go underneath with the least amount of trace as possible. So I'm going to go around here, move to the bottom, and go back to the top. So I only have one trace that I had to place on the bottom other than the ground plane. And I want to make sure that that trace is as short as possible so it doesn't interfere with the overall ground. I'm going to go ahead and press B to report, and you can see that it provided a clearance with the ground plane. So it looks like I'm done with the routing. Actually, I think I see another air wire. I'm going to go ahead and turn off all of the layers so I can see the air wires. And you can see there's only one here. So turning off all the layers gives you the ability to see anything that you may not be able to see because of all of the graphics that are on the screen at the same time. So I'm going to go ahead and show the copper layers again, and I will route this one. Now let's take a look at the silk screen, because the silk screen needs to be readable, and it also has to be outside of any pads or vias or holes. So I'm going to turn off the copper layer because that's actually not going to help us. So if we turn on the mask, we can see where the conflicts lie. So you don't want any silk screen that's going to be over any of these vias or any of the holes here or on top of any of these pads. Putting them relatively close to the pads or holes that they relate should be good enough. That's good. The FP1, C6, C4. All right, this one looks like it could be a little bit. The J2 appears to be conflicting with this hole here, so I'm going to go ahead and move that. I'm going to put it next to the 1 pin. Now this silk screen here is going outside of the board, so I want to remove these lines. We can double click on the component. And under the Generals tab, you can go to Edit Footprint, and it'll change this particular instance of the footprint. So I'm going to go ahead and remove these silk screen lines. if you have trouble selecting the silkscreen lines, you can hide all of the layers except for the silkscreen layer in this window. You can see here that it says editing J1 from board. This is the J1. Saving will update the board only, and it won't update the library footprint. We're going to go ahead and save changes, exit, and those lines do not appear anymore. Okay, now I'm going to go ahead and click on the design rules check icon, and I'm going to click on the run DRC button. And it looks like I have one error or warning, and it says that there is a track G&D on F copper. Length is 0.0071 millimeters, and that's a really small segment. So you can see where the arrow is pointing. If I go in close, you can't really see anything here, but there is a trace or a segment of the trace that is extremely short. It says that it has an unconnected end, which may be true. It may be some little tiny trace that you can't really see and that it's just pointing outwards. So we're going to have to delete that part of the trace. I'm going to go ahead and delete all markers, close, see if I can find this trace. I'm going to delete the via. Yep, you can see a little trace. It's a little bit of an outside circle here. If I select it, you can see that there is one little trace that appears. I'm going to delete that, and I'm going to put a via right there. Let's see if we run it and get that error again. Okay, 0 violations. So that worked. I'm going to go ahead and put all the layers back on. Identifiers for the assembly, which is under the fab layer. You can move those around. I'm not going to be messing with those at all. Since it's not really going to change the way the PCB is made, I can just turn those off if I want. Let's take a look at the 3D viewer and see what the board looks like. You can see that the copper is showing the copper traces, and on the back where we have that little short trace that connects the VCC. I'm going to go ahead and end the video here. This exercise should show you a good idea or introduction to what it takes to put a circuit together in this series. Even though we sometimes use evaluation boards or circuits already made in our projects, you can still go to the website of the manufacturer that develops the integrated circuit, and you can find out application circuit information to be able to create your own circuit for use in your projects. As I said before, in all of the upcoming projects, when I put more components on these circuits, I will be showing this exercise of what it takes to put the circuit together and show what the schematic looks like and what the board layout could look like. Obviously, there are many variations to this circuit. You can place the components in various locations and it will still work fine, as long as we are following sound electronic design guidelines, minimizing noise, crosstalk, high frequency, signal trace, reliability, and integrity. If you're still watching at this point, thank you so much for sticking around. I am really grateful. Stay tuned for my next video, which I'll be getting into half duplex UART with a servo. Thank you for watching.